Hey, my name is Murphy, and I'm presenting on Knowledge Integration 5, which is a radio system. And I will be talking about the radio system in relevance to all three of the junior level courses in spring 2018, which includes ECE 312, 332, and 342. So here is our power supply and management system. And you can see that we're going to be talking about the other side of the circuit that we talked about in Knowledge Integration 4. So instead of sending out a signal, we are now receiving a signal with our antenna. And so you can see we have this antenna and it's going through a diplexer, and then we're going to be filtering it and mixing the signal and overall trying to get it back into the form that we want it to be when we first sent the signal in KI4. So let's just start by talking about amplifiers in general. So overall, if we want to increase the gain, it's going to be inversely proportional to swing and to bandwidth. And to increase gain, normally we would increase GM or R naught, or the ratio of W over L, which is width over length. And we want to either just increase the width or the whole ratio of W over L in order to increase the gain. And as I mentioned before, our bandwidth is inversely proportional. So whatever we do to gain, the opposite will happen to our bandwidth. So in KI4 we talked about a dipole antenna, and if we assume a dipole antenna, it's very simple. We know that we can only receive parallel to the direction of propagation, and so this is what our antenna actually looks like in the circuit, which is quite complicated compared to a simple dipole antenna. And here we're assuming we have a microstrip transmission line, and it is going to be altered a little bit here in the circuit. So we have this microstrip, and we want about a 50 ohm impedance of our antenna, and the only way we can get that is if we include the fringing effects, because otherwise our impedance is going to be way higher than that, around like 92. And so we know that electrical length is equivalent to wavelength, and our physical length of the antenna is going to be small because we want it to be able to fit on like a small radio circuit board. So it's wrapped up a bunch to save space. And you can see here in the middle, one of the important components here is the balloon, which is balanced, unbalanced. And here it balances the signal between the antenna and the receiver circuit. So the length of the antenna can be calculated to be, or the wavelength is approximately half a meter. So we want our physical length, our electrical length to be equivalent to this wavelength here. And we can see that after the antenna, it goes through this diplexer, and down here at the bottom. And a diplexer is basically just a two-line multiplexer. So that way it can receive and transmit signals without any interference or being restricted in either direction. And now let's try to build a bandpass filter. In order to build a bandpass filter here, our best method is to take a low-pass filter and a high-pass filter. So let's first look at the low-pass filter here, and you can see that it has an input resistance, an output resistance, and a capacitor. And here's the gain, and here is our Bode plot where we have the lower signals, or frequencies, sorry, allotted through, and the higher signals being cut off. And this speed of transition depends on several factors, which we will talk about in a minute. And here is a high-pass filter. We didn't actually plot this in the KI pre-work, so I didn't put a plot here, a Bodhi plot of it. But it's basically you put the capacitor over here instead of with this one, this resistance here, and the output is still this impedance over this impedance for the gain. And now, if we cascade these, or the same thing to put them in series, we end up with this Bodhi plot, where we're cutting off the higher and the lower frequencies we don't want, just picking that signal that we are interested in. And the reason we do this is because there's tons of radio waves going on in the air around us, and we just want one specific signal. So we're going to limit our bandwidth to that bandwidth that we're wanting to receive. So that's why we use this bandpass filter. And looking on, we see that after the bandpass filter, we have a low noise amplifier, and this amplifies the signal from the bandpass filter. And then we're going to do some demodulation here, because we're taking a signal and trying to demodulate it into the original signal. We use this mixer right here. This is a mixer, and this it's a LC oscillator here, and we're going to take those and mix that signal with the input signal. And we're doing this in order to get the frequency back into the audible range, because when we're transmitting over radio, we're going to use a different, like much higher frequency than what the signal should actually sound like when we want to play it out loud or make it sound like the original signal. And then we have this baseband amplifier and low pass filter, and that's just going to increase the frequency a little bit, make it more stable, make sure it's in the correct phase. And then after the low pass filter, we're going to take out, we'll have removed the unwanted higher frequencies or any imperfections after the circuit. So thank you.